Hello everyone, and welcome back to Research for Beginners. In today's lecture, we're going to talk about reliability in research, one of the most important foundations of good measurement. If your data is not reliable, then no matter how advanced your analysis is, your results will be questionable. Don't worry, I'll explain everything step by step with simple examples, and by the end of this video, you'll clearly understand what reliability is and how it is tested. Before we begin, if you don't want to miss future videos that simplify research methods, SPSS, and data analysis, please subscribe to our channel, like this video, and follow us for regular updates.
Let's start with a simple question. What is reliability? Reliability refers to the consistency and stability of a measurement. In simple words, if we measure the same thing again and again, do we get similar results? For example, if a weighing scale shows your weight as 70 kilograms today, 85 kilograms tomorrow, and 60 kilograms the next day, without any real change, that scale is not reliable. In research, reliability means that our questionnaire, test, or instrument gives consistent results.
Now, let's look at this slide very carefully because it captures the three fundamental ways reliability is understood in research. Many students think reliability is just one thing, but in reality, reliability can be viewed from three closely related perspectives: stability, accuracy, error in measurement. All three are connected, but each asks a slightly different question about our data. Let's start with the first type, stability. Stability asks a very simple question. If I measure the same thing again at a different time, do I get a similar result? This view of reliability focuses on consistency over time. Imagine you are measuring an employee's productivity score. If the employee scores 85 today, 84 next week, and 86 the week after, the measurement is stable. But if the scores are 85 today, 60 next week, and 95 the following week, with no real change in work conditions, then the measurement is not reliable. In research, this idea of stability is usually tested using test-retest reliability. We administer the same test twice and correlate the results. A high correlation means the measurement is stable and reliable over time. Now, let's move to the second perspective, accuracy. Accuracy asks a slightly different question. Does the score I observe reflect the true performance or true value? Here, reliability is linked to how closely the measurement captures the true score. Imagine you are shooting arrows at a target. If all arrows hit the center, the shots are accurate. If all arrows hit the same wrong spot, they are consistent but not accurate. In research terms, a measure can be stable but still inaccurate if it consistently measures the wrong thing. Suppose a questionnaire is intended to measure job satisfaction, but most questions actually measure salary satisfaction only. The scale may give consistent results, but it does not accurately reflect the true construct of job satisfaction.
The third way to understand reliability is through measurement error. This perspective asks, how much error is present in my data? In classical test theory, we say, observed score equals true score plus error. Think about a person filling out a survey. One day they are tired, another day they are motivated, another day they are distracted. These temporary influences introduce random error. Now think of a weighing scale that is always 2 kilograms off. That error pushes the measurement in one direction every time. This is systematic error, and it seriously harms reliability. The more error we have, the further we move away from the true value, the less reliable our measurement becomes. This is why reliability is often defined as the relative absence of measurement error.
In this slide, we are answering a very important question in research methodology. Why do scores differ when we measure something? Whenever we collect data, whether from people, machines, surveys, or tests, the values we observe are not identical. These differences in scores are called variability, and this slide shows us that variability comes from two main sources: real differences, error variability. Let's start with the left side of the slide, real differences. Real differences refer to genuine, actual differences between people, objects, or equipment. Think about students taking an exam. Some students study more, some less. Some have stronger background knowledge, others do not. If one student scores 90 and another scores 65, part of that difference is real. This variability is not a problem. In fact, this is the variability we want to capture in research. Imagine two machines producing parts in a factory. One machine is newer and more precise. Another is older and slightly worn. Differences in output quality reflect real differences in equipment performance. Now let's move to the right side of the slide, error variability. Error variability refers to differences in scores that do not reflect true performance. These differences come from measurement errors, not from real differences. First, let's talk about random error, shown here as random fluctuation. Random error occurs because of temporary, chance factors. Again, someone answers a questionnaire. Today they are motivated. Tomorrow they are bored. Their responses vary slightly due to mood, not because the underlying attitude changed. Think of a weighing scale again that is always 2 kilograms too high. Every measurement is wrong, but it is wrong in the same direction.
Error and reliability are two sides of the same coin. More error means less reliability. Less error means more reliability. Our goal in research is always to minimize error so that our observed data is as close as possible to the true value.
This slide is extremely important because it explains the foundation of reliability in research. Everything we do later, Cronbach's alpha, test-retest reliability, split-half reliability, comes from this one idea. Every score has 3 components. Let's begin with the basic idea shown at the top of the slide. Any score we observe in research consists of 3 components: the observed score, the true score, the error. In simple terms, what we measure is never perfectly pure. The core equation, very important. The central equation here is observed score equals true score plus error, or in symbols, x observed equals x true plus error. This equation comes from classical test theory, and you must remember it. Observed score, what we actually measure. Let's look at the blue box on the left, observed score. The observed score is what we actually record, what appears in SPSS, what we analyze statistically. Example, if a student scores 85 in an exam, 85 is the observed score. But that 85 includes the student's real ability plus some amount of error. True score, what we are trying to estimate. Now move to the green box, true score. The true score is the actual level of ability, attitude, or performance, something we never observe directly. Example, a student's mathematical ability might be 82, but on the test day, they guessed one question correctly or made a careless mistake. So we never see the true score exactly. Research is always an estimation process. Error, y observed equals true. Now look at the orange box, error. Error represents random influences, fatigue, mood, distraction. Example, random error. The same student slept well, higher score, slept poorly, lower score. Example, systemic error. Again, a weighing scale that is always 2 kilograms off produces consistently biased results.
In this slide, we move from theory to practice. So far, we have understood what reliability means and why measurement error matters. Now, the key question is, how do we actually determine reliability in research? The answer is simple. We determine reliability by correlating sets of scores. This slide shows 3 main approaches used widely in research: test-retest reliability, parallel or alternate forms reliability, split-half reliability. Let's begin with the first method, test-retest reliability. This method answers one main question: is the measurement stable over time? How it works? The same test is given to the same group of people at 2 different points in time. Then we correlate the 2 sets of scores. A high correlation means the measurement is stable and reliable over time. Imagine you measure students' anxiety levels today. Then you measure the same students again after 2 months using the same questionnaire. If students who scored high the first time also score high the second time, and students who scored low remain low, then the test shows good test-retest reliability. However, this method has some challenges. People may remember their answers. Practice effects may occur. Real changes may happen due to learning, aging, or experience. So, a low correlation does not always mean the test is bad. It may reflect real change, not measurement error. Now let's move to the second method, parallel or alternate forms reliability. This method answers a different question. Are two equivalent versions of a test consistent with each other? Instead of giving the same test twice, we give two different but equivalent forms of the test, often called Form A and Form B. Both forms are similar in content, similar in difficulty, designed to measure the same construct. Scores from the two forms are then correlated.
Imagine two versions of a statistics exam. Exam A, Exam B. The questions are different, but they test the same concepts at the same difficulty level. If students perform similarly on both forms, the test shows high parallel forms reliability. This method reduces memory and practice effects, allows testing on the same day or close in time. The biggest challenge is creating truly equivalent tests. This requires time, expertise, careful test design. Now, let's look at the third method, split-half reliability. This method is especially useful when you want to measure reliability, but you can only administer the test once. A single test is divided into two halves, commonly odd-numbered items, even-numbered items. Scores from the two halves are then correlated. If someone scores high on one half and also high on the other half, the test is considered internally consistent. Imagine a 20-item questionnaire measuring job satisfaction. You split it into 10 odd items, 10 even items. If both halves produce similar scores, the scale has good split-half reliability. Because each half is only half the length of the full test, the reliability estimate must be corrected. This is done using the Spearman-Brown formula, which SPSS calculates automatically.
This slide introduces one of the most widely used reliability methods in research, the internal consistency method, measured primarily using Cronbach's alpha. If you are working with questionnaires, surveys, or attitude scales, this is the reliability test you will use most often. Let's begin with the idea at the top of the slide. Internal consistency asks a simple but powerful question. Do all the items in my scale work together to measure the same construct? In other words, are the questions consistent with each other? Are they all pointing in the same conceptual direction? Look at the checklist illustration on the left. Imagine you have a questionnaire with several items. Item 1, Item 2, Item 3, Item 4. All of them are supposed to measure one construct. For example, job satisfaction, technology acceptance, attitude towards sustainability. Internal consistency checks whether responses to these items are aligned. Cronbach's alpha, the core measure. The key statistic shown in the center of the slide is Cronbach's alpha, represented by the symbol alpha. Cronbach's alpha is, used for scale data, Likert-type items, a measure of internal reliability, a summary of how well items correlate as a group. Think of it as a single number that tells us how coherent the scale is. How Cronbach's alpha works, conceptually. Cronbach's alpha looks at correlations between every possible pair of items, and then averages these relationships. If items are measuring the same thing, they will move together. Their correlations will be higher. Alpha will be higher. If items are measuring different things, correlations will be weaker. Alpha will be lower.
Simple example, very important. Imagine a job satisfaction scale with these items. I enjoy my work. I feel motivated at work. I am satisfied with my salary. I like my colleagues. If people who agree with item 1 also tend to agree with items 2, 3, and 4, then the scale shows high internal consistency. But if item 3 behaves very differently from the others, it may be measuring something else and reduce reliability. One major advantage of Cronbach's alpha is that it helps us identify items that do not correlate well with others, decide whether to remove problematic items. Removing such items often improves reliability, but this must always be done with theoretical justification, not blindly. Although exact cutoffs depend on context, general guidelines are alpha greater than or equal to 0.80, good reliability. Alpha greater than or equal to 0.70, acceptable reliability. Alpha less than or equal to 0.70 may indicate reliability concerns. For exploratory research, 0.70 is often acceptable. For established scales, higher values are expected. The definition at the bottom of the slide is very important. Cronbach's alpha is equivalent to the average of all possible split-half correlations. This means, instead of splitting the test once, odd-even, Cronbach's alpha considers all possible ways of splitting items. That is why it is considered more robust than a single split-half estimate.
Is a higher Cronbach's alpha always better? Yes or no? Explain your answer in the comments. Drop a comment with the Cronbach's alpha value from your last study or assignment. Let's discuss whether it's acceptable. In the next video, we'll show you how to calculate Cronbach's alpha in SPSS and how to improve reliability by identifying weak items. Also, in our upcoming videos, we will discuss the difference between Cronbach's alpha and composite reliability, as well as the distinction between reliability and validity of data. Stay subscribed for future updates. If you don't want to miss future videos that simplify research methods, SPSS, and data analysis, please subscribe to our channel, like this video, and follow us for regular updates. We are building this channel to support early researchers, MBA students, and PhD scholars, and your support helps us continue creating clear, practical, and reliable research content. Comment below and tell us which research topic you want us to cover next.